Okay, folks, welcome to our pre-work on double integrals with polar coordinates. So before we jump into that, I want to make sure we're all comfortable with polar coordinates, so I'm going to do a quick review. So as a reminder, we do a lot of our math in the rectangular coordinate system, also called the Cartesian coordinate system, where we label these two axes, the two principal axes, as x and y. And one thing to mention is that this is a two-dimensional coordinate system, so we can think of it as being the same as R2. And if we were to label, say, this point right here, we label it with the coordinates x, comma, y. We're all real familiar with this. Let's pick another point here and just reiterate how we find a point. So if I were to talk about this point in our rectangular coordinate system, I need to give sort of a roadmap for getting there. And in fact, our work with vectors has kind of reiterated that. But one way to talk about the roadmap for getting there is we're going to say that these are the coordinates, say, 3, negative 2. And the way we interpret that is it says to move 3 units along the x-axis and then to move 2 units down on the y-axis. So that's something we've all done. Okay, so then what is the polar coordinate system? The polar coordinate system is another two-dimensional coordinate system, and it's given by, it's completely determined by this pole here, which we usually draw in the same direction as our x-axis, but I want you to keep in mind that this is not necessarily the same as our x-axis. We're thinking about this as being, this is one 2D space, and this is another 2D space, and we will move back and forth between these two different 2D spaces. So let's say we wanted to talk about, say, I don't know, this point down here. Well, we would describe how to get there by the coordinates r, comma, theta. So that's what our coordinates are as opposed to x, comma, y in the rectangular coordinate system. So let's talk about how we would get to, let's say, this point right up here. Well, one way to think about this is just the same way we gave a roadmap of directions for getting to this point, we'll give the roadmap 3, pi over 4. And the way we're going to interpret that is we're going to go 3 units. We're going to unitize this pole. We're going to go 3 units along this pole, and then we're going to rotate from that pole up an angle of pi over 4. And that's how, so there's our theta equal to pi over 4. That's how we would get to this point. Okay. So we think about moving out the pole's distance of 3 and then rotating up to the angle pi over 4. So here you can see I've given you a bunch of polar graphs. I've had to highlight these a little bit better so you can actually see the units because there's a couple of extra lines on there. So this first ring here corresponds to r equals 1, this second ring to r equals 2, the third ring to r equals 3, and you can see that this has got the principal angles on it from 0 to 2 pi. Of course, you can repeat yourself, continuing to spiral around this. Let's go ahead now and plot some points on this coordinate system. So the first one I want to plot is the ordered pair 3, pi over 6. And it's really important to keep in mind that these ordered pairs, they go like r, theta. Okay. So if we were to go, the way we could think about getting to this position is we're going to go out 3 units along our pole. So the pole's not very well highlighted here, but this is our pole in our polar coordinate system. And so we're going to go 3 units along the pole. So there's 1, 2, 3 units along the pole, and then we're going to rotate up to an angle of pi over 6. So we're going to rotate this position up to the angle pi over 6, and there is that particular point with the coordinates. Let me see if I can zoom in and label that with the coordinates 3, pi over 6. Okay. So I'd like to put 2 more points on here. I'll let you guys do the rest after that. But let's go ahead and put the coordinates 1, 5 pi over 4 and 1, negative 3 pi over 4. So to do the coordinates 1, 5 pi over 4, I'm going to go out 1 on my pole, and then I'm going to rotate to 5 pi over 4. Well, let's see here. Where's 5 pi over 4? That's about right. Well, that is right there. There's the angle 5 pi over 4. So I'm going to go and I'm going to take and rotate this around to the angle 5 pi over 4. So there are the coordinates 1, 5 pi over 4. Okay. That might be a little hard to read. I'll just label them out here. 1, 5 pi over 4. So the other thing I want to mention is that these coordinate systems are not, in this coordinate system, the points are not unique. There are many different ways we could label a particular point. So for example, we could go to, we could again go out 1 on the polar axis. So let's go out to 1. I'll label that in black here. And now we're going to rotate an angle of minus 3 pi over 4. So let's rotate into the angle of minus 3 pi over 4. And lo and behold, we land on the same point. So that's something to keep in mind, is that these points are not given, there's not one fixed way of describing these points like there were in the rectangular coordinates. But we just work with that, and usually what we do to alleviate that is we talk about things being in the, we talk about the principal angles. We start from 0 to 2 pi as we need to. Okay, so I'm going to let you guys pause the video and finish plotting these remaining 3 points. So hopefully you tried this on your own. I went ahead and labeled these points D, E, and F, and then I've plotted them up here. You'll notice that D and E are both at the origin. The origin is a peculiar animal in that the radius is always 0, but any angle will work for the origin. And then here for point F, the way we think about it is we go out 1, we rotate an angle of, rotate an angle of pi, or I think actually I was supposed to go minus pi, so went out 1, rotated angle of minus pi, but then we multiplied that by a -1, which lands us right here at the, so this is the, we could think of this as the coordinates -1 comma minus pi, or more commonly known as the coordinates 1 comma 0. Okay, so the next thing I want to do is I want to sketch the graph of 3 familiar objects in the polar coordinate system. The first thing I'm going to do is sketch a graph of r equals 2. And actually you can see, because of the way I've labeled this, for sketching r equals 2, that is just a circle. For any choice of theta, the r value is 2. And so there's the graph of r equals 2 in the polar coordinate system. It's the graph of that function. Okay, let's do the graph of theta equals pi over 3. So that says that regardless of our choice of radius, we could pick different radial values, the angle that we must always go out is pi over 3. So for example, we could go out the radius of 1 and then move up to the angle pi over 3. Or we could go out to the radius of 2 and then we rotate up to the angle pi over 3. Or we could go out the radius of 3, rotate up. We could even go out 1 and then go out 1, rotate up pi over 3, and then multiply that result by -1 to give us the coordinates -1 comma pi over 3. And so you'll notice that all of these points are lying along a line here, and sure enough, the graph of a line in the polar coordinate system, so there's the graph of of theta equals pi over 3. So a line in the polar coordinate system is just given by an angle. Okay. The last one I want to sketch, and we can do blue here, the last one I want to sketch is the graph of r of theta equals sine of theta. Okay. So what I recommend doing for something like this, if you don't know what the graph is that you should build a table of values. So let's make an r and a theta. And even though, by the way, I want to mention this, we give our coordinates in terms of r comma theta. And we always do it alphabetically that way, r comma theta. But when we give our functions in polar coordinates, we typically think of theta as the independent variable and r as the dependent variable. So I'm going to build my table of values here, but instead of picking values for r and finding theta, I'm going to pick values for theta and find r. So for example, when theta equals 0, if I take the sine of theta, take the sine of 0, I just get 0. And when, let's see here, we could do a couple more. When theta equals, say, pi over 6, then the radius is 1/2. And when theta equals pi over 4, then the radius is the square root of 2 over 2, and we're just outputting the sine values. If we go ahead and start sketching these on our graph up here, let's see here, we had the coordinates 0, 0, okay? And then for the angle where pi is equal to 6, we had a radial value of 1/2, so that's right there. And for pi over, sorry, I put that on the pi over 3 line. I don't know if I'm going to be able to get that off. No, just bear with me, pretend it's not there. And let's put that in the correct location. So I'm plotting this point right here. So we go to the radial value of 1/2, and we plot and we rotate up pi over 6, and that's that point right there. Let me plot this one now. So we're going to go to the angle pi over 4, which is midway between those two, and then we go to the square root of 2 over 2. That's a number like 0.707. So let's see here, that puts us right about here. And let's just do one more. when r is equal, or when theta is equal to pi over 2, the radius is 1, and that puts us right here. And I don't think it's very clear at all at this point, but if you continued plotting more points, we would see that this would sketch out the circle with a radius of a half, a diameter of 1, and it's oriented this way. So that's the graph of r of theta equals sine of theta. Okay, great. There's one more graph that I want to do, and that is the graph of this function right here. And I'm going to graph it in the third coordinate system. I want you to pause the video and build an r theta ordered pair, just like I did for the graph of our circle, and then go ahead and plot those points on this coordinate system here and see what we would end up with. Sorry folks, so to make our lives a little bit easier, to make it a little bit easier to sketch this and see this, I've gone ahead and adjusted the scale. So this is where r equals 1, this is where r equals 2. So what I want you to do now is build a r theta ordered pair tree, just like algebra 1, r comma theta. Pick various values for theta, plug them in, and then graph this function. So folks, what I've done here is I made a table of values. I plugged in various values for theta, plugged in 0, it spat out r, we got a, I called that point a. I plugged in pi over 4 for theta, and it spat out the square root of 2 over 2, etc. So you can see I've got this table of values. I went ahead and labeled the points a, b, c, d, e, and I've got those points drawn up here on our graph where they belong. And now I'd like to go ahead and sketch the graph of this function. We haven't plotted enough points yet, but I'll be able to use symmetry to help me finish this out. And that's a pretty ugly graph here. Okay, and if we continue this out, this point, the mirror image of this point would be down here, and then here we've got c is 1, and then we've got at 3 pi over or pi over 4, we're at 0.707, so it should be more about right there. And there, approximately, we have the graph of this function. It's a pretty bad sketch, but the graph of this function is called a cardioid. So folks, we're actually going to use this graph later on in this segment. I'll give you a better image of it when we get there. So folks, if you have any trouble with this, please let me know, but do make sure that you're comfortable doing some very basic sketching in the polar coordinate system. Thanks.